So, good morning, everyone. I am Rupesh of GM University, pursuing my BTech in CSE AIML second year. So, these are my teammates Sahil, Shivkumara BC, Rohan DR, Rohit Itigi, and Lokesh. So, today we'll be discussing on a topic which is LoRa-based environmental monitoring, in which we design a LoRa-based system to monitor air quality, temperature, and humidity over a long range, stimulating real-time environmental data collection. So I request Sahil to please share the screen and put the PPT on the screen. So as we come to this topic, so firstly we are going to see the introduction part of it. So what is LoRa? So LoRa stands for long range, a wireless communication technology. It means that it is a technology which is used for wireless communication in a long range. It is designed for long-range communication with lower power consumption, making it suitable for IoT applications. So, importance of environmental monitoring. Climate change. Accurate data helps track and address global climate changes, which will be very useful. Secondly is pollution control. Monitoring air quality ensures effective management of pollutants. Thirdly is public health. It provides critical insights to mitigate health risks related to environmental factors. Sahil, could you please change the slide? And in the above slide, we see the objective of this system. The goal is to design a system using LoRa technology for effectively monitoring of environmental parameters such as air quality, temperature, and humidity. As we move on to the next slide, advantages of LoRa technology. So the first thing is it covers long range coverage. It has long range coverage. It operates up to 15 kilometers in rural areas, suitable for long scale developments. Low power consumption. It enables long battery life for sensor nodes, reducing maintenance. Multi-sensor capability. It supports multiple sensors in a single network. And the last is real-time and periodic data transmission. It allows for both instant updates and scheduled monitoring. Sahil, could you move to the third slide, please? So the system design overview. Over here, we are going to see the components used in this LoRa technology. So firstly, LoRa transmitter nodes. These nodes are equipped with sensors for air quality, example PM 2.5 to PM 10, and temperature and humidity sensors. They are used to collect and transmit data wirelessly. The second is LoRa Gateway. It aggregates data from transmitted nodes and it sends the data to the cloud via Wi-Fi, Ethernet or cellular networks. Thirdly, it is cloud platform. It stores data for a long-term use and it processes and analyzes real-time data for actionable insights. The last one is user interface. It provides a visual representation of data through a web or mobile app, and it allows users to monitor and manage environmental conditions easily. So the next topic will be explained by my friend Rohan DR. Thank you.
Thank you, Rupesh. Let's move to next slide. It is hardware components. These are the hardware components. The first hardware component is sensor. Air quality has two sensors. MQ135, it is a low-cost gas sensor used to detect gases like ammonia, benz, and carbon dioxide. The second sensor is STS011. It is a laser-based particulate matter sensor designed to measure PM2.5 and PM10, which are critical indicators of air pollution. Temperature. There are two sensors. DHT22. It is a digital sensor that measures temperature and humidity. It is accurate and widely used in DIY and professional projects. The second sensor is BMP280. It is a pressure sensor that provides temperature readings. It can be used to measure altitude and atmospheric pressure changes. Humidity. There are also it also two sensors. For the first sensor is DHT22 and AM2302. These sensors are essentially the same sensors model with slightly different packaging. They are digital sensors providing accurate humidity measurements. The second component is LoRa module, SX1278 or RFM95W. These modules use long-range technology for wireless communication. The third hardware component is microcontroller. Arduino, a simple and cost-effective option for basic sensor integration and data transmission. ESP32, a more advanced microcontroller with built-in Wi-Fi and Bluetooth, suitable for IoT applications. Raspberry Pi, a single board computer that offers more computational power, suitable for more complex tasks like processing and visualization. Next component is power supply. Solar powered options for sustainability. Sahil, can you move to the next slide? Next slide. These are the software components. Uh, the first component is programming language. C, Python, Java, and etc. LoRaWAN protocol implements secures bidirectional communication. Cloud platforms. AWS IoT, Google Cloud, or Think Speak for data visualization. The last software component is data processing tools. MQTT, it is used for lightweight communication. Sir, can you move to the next slide? These are the implementation steps. There are 5 steps. The first step is sensor integration. It connects and calibrates sensors with the microcontroller. The second step is LoRa communication setup. It configure LoRa modules for data transmission. The third step is data transmission. It sends sensor data to the long range gateway. The first step is cloud integration. It pushes the data from the gateway to the cloud platform. The fifth step is user interface development. It creates a dashboard to display environmental data. And the remaining part will be explained by the next slide is explained by Lokesh.
Let's move to the next slide. Real-time data simulation. First one, data collection. Simulate air quality, temperature, and humidity readings. Next one, visualization. Example graph showing trends over time. Example is line or bar charts. Next one, challenges and solutions. First one is challenges. Signal interference in urban areas, power management for remote sensors, data accuracy and calibrations. Solutions. Use repeat cut mud. Use repeaters or mesh networking. Deploy energy efficient components. Regular calibration of sensors. Next one. The code will be explained by my friend Soil.
Thank you, Lokesh, for explaining the challenges and solution. Now I am going to explain the code. Header files. In the line number 1, include spi.h. Here, the spi.h library is included to enable SPI communication. SPI is a communication protocol used to exchange data between a microcontroller and external device like a LoRa module. This communication is synchronous and allows high speed data exchange. The LoRa module communicates with the microcontroller over SPI. In the line number 2, include LoRa.h. This library provides the necessary function to communicate with the LoRa module. LoRa is a wireless communication protocol designed for a long range, low power data transmission, often used in IoT application. Pin defined for the LoRa module. In the line number 5, hashtag define SS10. This line defines the slave select pin as pin 10. In SPI communication, the SS pin is used to enable or disable the LoRa. Setting this pin low enables the LoRa module, while setting in high disables it. In the line number 6, hashtag define RST9. It defines pin 9 for the reset signal. The reset pin is used to reinitialize the LoRa module in case of errors or for stirring the fresh. In the line number 7, hashtag define DIO2 defines pin 2 as the DIO0 pin. This pin is often used to signal events like packet reception or transmission completion by the LoRa module. Mock sensor data. In the line number 10, flow temperature is equal to 24.5. It creates a simulated temperature value of 25.5 degrees Celsius. This mock data represents the temperature reading from a sensor. It's used for testing the LoRa communication system before actual sensors are connected. In the line number 11, float humidity is equal to 60.0. It creates a simulated humidity value of 60%. Similar to the temperature variable, this represents mock sensor data for humidity in the environment. And in the line number 12, int air quality is equal to 150. It creates a simulated air quality index value of 150. AQI is a measure of air pollution. A value of 150 generally indicates unhealthy air quality. These mocks values are placeholders to test data transmission without connecting actual sensors. And in the line number 14, void setup. The setup function runs once when the microcontroller is powered on or reset. It is typically used to initialize hardware components and configuration. In the line number 15, serial.begin 9600. It initializes the serial communication interface with a baud rate of 9600 bits per second. This is used to send and receive data between the microcontroller and the computer for debugging or monitoring. In the line number 16, while serial waits until the serial monitor is connected. This is useful during debugging to ensure the messages printed by the microcontroller are displayed properly on the serial monitor. And next, in the line number 18, serial.println LoRa environmental monitoring. It prints the message LoRa environmental monitoring, the serial monitor. This indicates that the program has started and is ready to begin initialization. LoRa module initialization. In the line number 21, LoRa.setPins SS RST 0 configures the LoRa module with the previously defined pin number. This step is necessary to ensure the microcontroller can communicate with the LoRa module over SPI using correct pins. In the line number 22, if LoRa.begin 915E6, it attempts to initialize the LoRa module with a frequency of 915 MHz. Here, 915 MHz is the operating frequency for LoRa in North America. If the initialization fails, the code inside the if block will be executed. In the line number 23, serial.println LoRa initialization failed. The LoRa module fails to initialize. An error message LoRa initialization failed is printed to the social serial monitor. This helps the user diagnose hardware or configuration issues. And in the next line, line number 24, while 1. This creates an infinite loop to the halt the program if LoRa initialization fails. The microcontroller will remain in this state until it is manually reset. At last, in the line number 26, serial.println. LoRa initialization successful. If the LoRa module is initialized successful, a success message LoRa initialization successful is printed to the serial monitor. And in next, my friend Rohit will continue the remaining part of the code.
Thank you, Sahil. As you move on to line number 29, the void loop. The loop function in Arduino runs continuously after the setup function is executed once. Every time loop finishes, it starts over. And as you go on to line number 31, 32, 33, temperature plus equals random minus 5 comma 5 multiplied to 0.1. Here adds a random change between minus 0.5 celsius and plus 0. Plus 5 to temperature, and humidity plus equals random minus 2 comma 2 multiplied to 0.1. Here adds a random change between minus 2 percentage and plus 0.2 percentage to humidity. And the line number 33, air quality equals random 100 comma 200. Here it generates a random AQI value between 100 and 200 for air quality. As we move on to line number 36, the string message. Here the string temperature comma 1. This converts the temperature variable into string, rounding it to a one decimal place. And the line number 37, string humidity comma 1. Here it converts the humidity value into a string, rounded to place one decimal place. And the string air quality, here it converts the air quality to a string. As you move on to line number 41, LoRa begin packet begins the transmission of new LoRa packet, and this prepares the LoRa module to send data. And the line number 42, LoRa print message, which sends the message string over the LoRa network. And the line number LoRa end packet ends the packet and sends the data. This function.
Start.
Hmm.
Start.
As you go on to line number 46, serial print ln. Here this line prints the message to the Arduino serial monitor so you can see what data is being sent. And this helps you debug or monitor the data being sent over LoRa. As line number 49, delay 5000. This line executes the program for 500 milliseconds, which is 5 seconds. Before it repeats the loop, the delay ensures that you can send data too frequently. Without this, the loop would run as fast as the microvalent. And the next slide will be proceeded by my friend Shivkumar.
Thank you, Rohit. So this is the output of our code. Uh, Rohit, could you please move to the next slide? So benefits of the system. So this slide highlights the benefits of our system. Here, long range monitoring, ideal for rural and urban applications. First, it supports long range monitoring, making it suitable for both rural and urban areas. So second one, cost effective, lower operational costs compared to cellular network. So here second, it is cost effective as it has lower operating costs compared to cellular network. And next one, real-time insights enables timely actions for environmental issues. So finally, it provides real-time insights, allowing quick actions to address environmental problems. These features make the system efficient and practical. So Rohit, could you move to the next slide? So future scope. This slide explains how our project can improve in the future. So first, scalability. Expandable to include more environmental parameters. Example, carbon dioxide, noise levels. So first, it can be explained to monitor more environmental factors like carbon dioxide and noise levels. So second, AI integration, use machine learning for predictive analytics. So second, we plan to use AI to predict issues and provide better solutions. So next, IoT expansions. connect with small city infrastructure. So third, we aim to connect it with smart city systems for seamless integration. These upgrades will make the system more useful, smarter, and future ready. So Rohit, yeah. Now, so this is the conclusion part of our program. So so this slide concludes our project. LoRa-based monitoring is a robust solution for real-time environmental data collection. So LoRa-based monitoring is a strong and reliable way to collect real-time environmental data. It provides useful insights that so provides actionable insights for improving public health and environmental safety. So it provides useful insights that can help improve public health and ensure environmental safety. So next, explore further development and collaboration opportunities. So finally, it opens doors for further development and opportunities to collaborate with others to make it even better. So this is the end of our project. And thank you everyone for hearing us. And thank you, Sanjay sir, for giving us the opportunity to do this project. Yeah, thank you, one and all. Thank you, my teammates.